Okay, let's start. It's a bit more sparse today. Is there like a midterm or something? Oh, okay. Yeah, makes sense. What midterm is that? What midterm is that? Okay, yeah. Pretty fun. Okay, morning everyone. So we finished talking about M3 last lecture. Actually, how's M3 going? It's like good, bad. Do you guys think an extra day would help? Like, I don't know if you've, probably?
Like, we did A-star, but like, we're still failing performance.
Okay.
So there's something wrong.
Yeah. I'll make a post on Piazza. Maybe like we can make it until Monday instead of Sunday. Sounds good. Okay, so yeah, we finished talking about M3, and now we're going to start talking about milestone 4, which builds on top of what you learned in M3, but now like it's getting into more like real-world problems and how to optimize for certain objectives, okay, where you cannot find an optimal solution in a reasonable time. So the problem is that you're gonna act like as a traveling courier company, and you're basically trying to optimize the delivery schedule of like a truck, where you are given a certain number of deliveries to make with pickups, drop-offs, and where to take the truck from and to park it. So you are given, sorry, just a second, yeah. You are given a certain number of depots. These depots basically tells you where you can pick up or drop off a truck, like at the beginning or at the end of the day. So you can start at any depot, you can end at any depot, it's up to you. And you are given, we call this variable n deliveries, where each delivery is marked by a pickup intersection, marked here with the up arrow, and the drop-off intersection marked here with the down arrow. So in this case, we have 4 deliveries to make, A, B, C, and D, okay? And the problem is asking you to find a delivery route for the truck for the whole day, such that you can pick you can pick at any certain time, you can pick one of these deliveries, drop it off. The only constraint is that you cannot make a delivery until you have picked it up before, right? So you can do the deliveries in any order. You can pick multiple packages at the same time. It's up to you by visiting different intersections. And the overall goal is to optimize for the travel time of the truck. Okay? So, sorry, go ahead.
Is there like a constraint where it's like you can only have 2 packages at a time?
No, so in previous years we had this called capacity constraint where like the truck can fit as much, but it's just made it a bit more complicated. It's kind of the same approach to the solution, but you have to add like in your code these. So we change it, we mix it up from year to year. So in this year, no, we don't have this capacity constraint. Okay, so yeah, so in milestone 3, we were given like 2 intersections, and you're trying to find the optimal path, at least when the turn penalty is 0, to go from intersection A to intersection B. In this case, you have multiple intersections, and you have an extra constraint is in that you cannot drop off a package unless you've picked it up before. Okay, so this is optimization like a real world problem. And there are all sorts of logistics companies that do these things. For example, how to schedule Uber drivers, how to schedule food delivery, flight schedules, etc. All of these are kind of a variation of this problem. And most of the research problems that like PhD students work on are kind of problems similar to this. We're gonna delve into like what is a computationally hard problem in a little bit, and you will like notice that you cannot find an optimal solution of these problems in a reasonable time. Okay. So we're gonna mark the number of depots by D from now on, and the number of deliveries to make by N. Okay, so in this case we have 3 depots and 4 deliveries. Okay, yeah, and as I said, you have to pick up each package before delivering it. That's the only constraint you have to make. Okay, so let's see, is this a possible solution? So we started here at this depot 1, for example, and we went to this intersection, which is dropping off B and then picking up D. Is this a possible solution? No, because yeah, we cannot drop off B before picking it up. Okay, so again, remember that this is the only constraint we have. So this is another, I think, more legal solution. We call this a legal solution. And we start at depot 1 again. we go pick up D, drop off D, pick up B, then we pick up C because we found that like it's closer. And then we go all the way here on the 401 to drop off C, then pick up A, drop off B, and then drop off A. So and in this case, we ended up at depot 0. We could have ended up at depot 1 as well. It doesn't matter. Like we are free to choose the depot that we want to, as long as like it minimizes the travel time of the courier. Okay, so what is the output? Like in milestone 3, your output was just a sequence of street segments, which represents the path from intersection A to intersection B. In milestone 4, your output is a collection of those. So in each one of milestone 3 output is going to be under a courier subpath struct. The struct basically tells you that I'm starting at a certain intersection, I'm ending at a certain intersection. All these intersections correspond to one of the given intersection inputs, and this is the vector of, or the path to go from this start intersection to end intersection. And then you're gonna have a collection of those which represents the overall travel route of the truck. Okay, any questions on this? Do we understand the basics and the specs of the problem? Okay, I'll take that a yes. So it's always good idea to get something going first quickly. This is an agile development, so you might not have the whole idea or like the whole plan from the beginning. Let's just try and get something working first and try to optimize on it or improve on it further. So the simple solution is to just reuse the milestone 3 pathfinder, the algorithm that you've developed in milestone 3, or you're still developing. So I'm just gonna say like, this is just a very simple solution. I'm just going to say, for example, I'm going to go to the first depot to the, from the first depot to the first package to pick up. So even if I'm given like depots, I'm just gonna ignore all of them and just take the first one. This is where I'm going to start at. And then I've decided to choose like just the first delivery in the order that they are given to me to go to pick up that delivery first. And then I'm calling here the find path. This is the path finder function that you're developing in milestone 3. And then we're going to loop from 0 to n-1, where n is, again, the number of deliveries. So since we've picked up the first delivery first, we're going to visit the drop-off of that delivery. Okay, so we're gonna add it to the overall path. And then from that first delivery, I'm going to say that, okay, I'm going to now pick up the second delivery in order. So I'm given the deliveries in a certain order in the input. I'm just gonna visit them one by one in order. Again, this is probably not a very good solution, just like a simple solution to get like us going and try to implement something. Okay, so once we pick up the last package, we need to return it to the drop-off location. So we go to the n-1 drop-off from that pickup intersection. And finally, we need to go to one of the depots. Again, I'm choosing here depot 0 and ignoring the rest. Okay? So here is the solution for this. Let's see. So we choose depot 0. We go pick up A. And then we go all the way here to the other side of the city, drop off A. Because again, I'm trying to just deliver them in order. And again, after A comes B. So I'm going to go all the way back again to pick up B, okay, and then drop off B, and so on, pick up C, drop off C all the way in the other side of the city, pick up D, and then drop off D. And then at the end, I'm just returning to the same intersection or depot intersection, which is depot 0. So is this a good solution? Like, yeah, it's clearly like not a, I wouldn't give an Uber driver a very good tip for this because he's going all over the city trying to pick up people. Yeah, go on. Yeah, that might be possible. Like, yeah. Like you're allowed to pick up the truck at any depot and drop it off at any other depot. It's not just about that. It's that you have to control the order you're visiting these intersections to minimize the overall travel time. Okay, and we're going to see that you need some kind of like intuitive ideas or like what we call heuristics to try and make the solution better. In this case, we just decided that we're going to visit these deliveries in order. And this is the route that we got. It's obviously not a very good route because it's like going back and forth between the two different sides of the city and it's like wasting a lot of time. So lots of wasted travel. We could have done this in a much shorter time. Does that make sense? Okay. So a more logical solution, for example, would be start at a certain depot. Like in this case, we started at depot 1 instead of depot 0. And since D is very close to us, it's a pickup intersection. So we're going to visit D pickup and then drop off D, go pick up B, pick up C because they are close to each other, and then drop off C at the other side of the city, and then while on the way, pick up A because it's close to us, drop off B, drop off A, and now you're free to choose whatever. So we're going to choose this intersection because it looks like it's closer in terms of travel time. Okay? Make sense? So we need to, again, we need to optimize the delivery order. So you can choose to visit these intersections in any order you want, as long as each pickup, for each delivery, the pickup intersection is visited before the drop-off intersection. By the way, you can visit the same intersection multiple times, doesn't matter, but like you only need to, like the truck works in a like very fast way. So once you visit an intersection, you're gonna pick up all of the packages that can be picked up there. So in your handout, we mentioned that a pickup intersection can appear several times for different deliveries. It doesn't matter. So you can visit that delivery, that intersection multiple times, or you can visit it once. It's up to you. Make sense? And our goal is to optimize the order of those intersections visited so that the summation of the travel times to visit from each intersection to each other intersection is minimized. Okay, so first, we need to see, can we do this perfectly? So in milestone 3, obviously, we've used Dijkstra, and Dijkstra helps us to do, like, find the path between two intersections perfectly, as long as, let's say, the term penalty is 0. It guarantees optimality. Can we do this here? So let's see. This problem is a variation of the popular problem called the traveling sales problem. Have you heard of this? Okay. So if you haven't heard of this, basically the idea is that you're given multiple cities around the world, or like in one country, for example, and you're starting at a certain city. It tells you that you need to visit each city at least once and end up at the same city that you started at, while minimizing your travel time. Okay, so in that problem, there is no constraint in terms of like you have to visit certain intersections between the other. And this problem you have because you have to pick up the delivery before it's dropped off, but it's kind of the same problem. And this problem turns out it's a very computationally hard problem, and you cannot build a perfect solution from smaller solutions. So in Dijkstra, when we're doing this wavefront, for example, wavefront expansion, we can prove mathematically that if you find a solution, an optimal solution of a smaller problem, like to visit one of the intersections within the smaller wavefront, then using that solution, you can expand on top of it and to find an optimal solution for a further intersection. And that can be proven mathematically. Unfortunately, with these kinds of problems, it cannot. So in milestone 3, we can prove optimality. In this milestone, or the problem that we're tackling in this milestone, we cannot prove optimality. Okay, so there isn't a quick algorithm that can guarantee that we find the perfect or the best solution or that achieves the minimum travel time of the truck. So why not try all solutions? Like we can do just an exhaustive search on all combinations of all kinds of orders of intersections that we can visit and try and see which one achieves the best travel time by evaluating it with our milestone 3. Okay, then we pick the lowest travel time. If this works, then we don't have to do milestone 4, and it's an easy solution. But let's see how many combinations we have. Okay, so we are given D truck depots to start or drop, to start or end at, and we are given n deliveries. Okay, so for n deliveries, we have two intersections for each delivery. One a start to pick up and one to drop off. So we have in total 2 n intersections, and we are picking one of the D starting locations, okay? So we're just trying to count the number of combinations that we can visit these intersections. Then we're gonna pick one of the 2 n pickup drop-off intersections. For simplicity, to simplify the math, we're just gonna ignore the constraint that we have to pick up before drop-off, and we're saying that you can visit any intersections right now, okay? You can say that once we found the best solution, you can just ignore it if it's not legal. Okay, so we're going to pick up one of the D locations first, and then we're going to pick up one of the two N intersections. Then, once we pick up the first intersection out of the 2N, we're going to pick up the second intersection out of 2N minus 1, right? Because we are left with 2N minus 1 intersections. So we repeat this until we finish all the deliveries or we finish all of the intersections that we need to visit. So, and then drop off at the closest depot again. This can be, you can choose out of the D intersections, right? So what do we have here? We have D times 2N times 2M minus 1 times 2M minus 2 up until times 1, right? So actually, it can be D squared because you're picking up one of the depots at the beginning and picking up one of the depots at the end. But let's simplify the math. So now we have D times 2 to the N factorial, okay? This is the number of combinations that we can loop over to find the best solutions in the, for the truck, right? So again, some of these might be illegal, but just for simplicity, we ignore the legality check for now, and you can check it later. Okay, so say like in this milestone, you are given like problem sizes that are on the size of 200 deliveries. But let's say for the sake of simplicity, we're gonna get like 100 deliveries with 10 depot intersections to start at, okay? So if we calculate this number, you can't probably calculate it on the normal calculator. You're gonna get a very big number, 10 to the 377, okay? So for each one of these for each one of these combinations, you're going to invoke the find path 2n plus 1 times. Why? Because you're trying to find the path to go from one intersection to the other using the algorithm that you built in milestone 3. Okay, so in this case, let's say that you've had a very good implementation of milestone 3, and you were able to achieve like 0.1 seconds per code. This is actually a very good implementation if you're able to do it. So let's now calculate the overall time that's going to take us to find the solution. So 10 to the 377 times 201 times 0.1 seconds, and that's around 1.6 times 10 to the 378 seconds, okay? If you look at the, and that translates to 5 times 10 to the 370 years. If you look at the lifetime of the universe, it's actually 14 times 10 to the 9. So this number is significantly longer than even the lifetime of the universe, so you probably can't even find the best solution like while the Earth is alive, right? So yeah, again, this is a variation of a popular problem called the traveling salesman problem. And this problem is known to be computationally hard because we saw that we cannot find an optimal solution in a reasonable time, okay? So all of the computationally hard problems tells you that when we say a problem is computationally hard, that means that there is no algorithm that can achieve the best solution or like the perfect solution within a polynomial time. What do we mean by polynomial? Polynomial basically in terms of the where your variable is n here, which is the number of deliveries to make. So for whatever k you choose, even if you choose like k equal 1,000 or 100,000, there is the solution to achieve optimality is always going to be bigger than asymptotically O of n to the k, okay? So computationally hard problem, we cannot find a solution that is in polynomial time. This means that at least we are going to find a solution in 2 to the n time, okay? And this is get very big. So whenever you increase n by 1, your computational complexity is going to double, right? Because this is an exponential complexity. So we need what we call heuristics in order to solve these problems. Heuristics are just like smart, educated guesses to guide the problem to find a good solution, what we call a good enough solution. It might not be the optimal solution. We cannot prove that it's going to be the optimal, but we can live with that as long as we can find the solution quickly, okay? And there are obviously heuristics that are better than others in terms of achieving better quality of results or better traveling time in this case. But we're going to study how to develop one of these heuristics. Yes?
Can you explain those two bullet points? Like, how did you come up with that complexity of n to the k and to the
So, yeah, This is outside the scope of this, but basically in, I think, ECE345, you're going to study that there is a class of problems called NP-complete problems. These are computationally hard problems, and you cannot prove that you can find a solution in polynomial time, and you can reduce one of, if you are given one of these problems, you can reduce it to any type of other problems. And one of these problems can be proven that it's going to take 2 to the n time complexity. And that's why we use 2 to the n. It might not be exactly 2 to the n in our case, but it's like some constant multiplier of this, right?
And what was the problem class called?
It's NP-complete problem. There is a slide about it in a bit, okay? Yeah, it's a very popular class of problems that people have been studying since the 60s, and they cannot find a solution, okay? So most research problems are computationally hard and actually are NP problems. For example, we've talked about in the previous lecture how in FPGAs they try to route some number of nets, and we know that we can route one net optimally, but we cannot route, or we cannot find the optimal solution in a reasonable time for when we are routing like 40 millions of those wires. Okay, so that's kind of an NP-complete problem. It's used in integrated circuits. It's used in drug design, transportation network design, for example, to schedule like flights how to go for a certain airport, or to schedule deliveries in this case. It's also used in medical applications. For example, in my PhD research, I was studying how to optimize the planning of a certain cancer therapy. And that planning, like, the problem on the hand was an NP-complete problem and computationally hard. So we had to come up with heuristics on how to find good solutions in reasonable time. Okay, so if we can find optimal solutions of these, PhD students probably wouldn't exist in computer science because they don't need, like there aren't any problem to work on. But in academia, most of the PhD students are basically working on one of these kinds of problems and trying to find a better solution than what is found in the literature and try to publish it. Okay, so, and this is a good segue to one of the popular pioneers in this field. His name is Stephen Cook. He's a U of T professor here in the computer science department. And he's a pioneer in the complexity theory studies. This complexity theory basically studies the computational hardness of problem and what is the difficulty of certain kinds of problems, okay? So his life story is like a bit interesting, so I'm gonna give you some information about it. So again, as I said, there is a certain type of problems or a class of problems called NP-complete problems. And these problems are computationally hard to solve. We know that they are computationally hard. No one has ever been able to prove that there is no solution that exists in polynomial time, but no one was able to find a solution, so it probably doesn't exist, okay? And Stephen Cook, what he did is that he proved that if there is a method to solve any of these problems in polynomial time, then you can solve any other problem in polynomial time as well, right? And this is a very popular paper. He, I think, published it in 1971. And it's basically the basis of computer science and complexity theory when it comes to computationally hard problems. Okay? So yeah, again, if there is one method that can be solved in polynomial time, then all the methods or all of these problems can be solved in polynomial time. And this is a famous debate in computer science called P versus NP. If you are able to prove P, where P is the set of all the problems that can be solved in polynomial time, and NP is all of the set is the set of problems that cannot probably be solved in polynomial time. Okay. However, as I said, no one has been able to mathematically prove that there is no solution that exists to solve these problems in polynomial time. But no one was able to find a solution. So there is this debate that P versus NP. If you can prove that one of these problems can be solved in polynomial time, then P is equal NP, and you're going to probably be very rich because you're going to be like very famous that you've been able to prove it. Okay, so if you're like, if you want to join like a high-risk graduate studies after you graduate and go try and find a solution for this or try to prove this, you're probably going to be very famous, but it's more likely than not you probably won't be able to prove it, and that's why it's a very high risk, right? People have been trying to prove this since the 60s, and not even one single proof has been no single person have been able to prove this, okay? So the interesting thing about Stephen Cook is that he was denied tenure at University of Berkeley in 1970. Okay, so in academia, if you don't know, professors work for the first like 6-7 years, like they work a lot, they try to publish a lot of papers and try to like prove to the university that they are good enough to stay. And then once they get this tenure after 7 years, they are hired for life, for their lifetime. They cannot be fired, okay? If they don't get tenure, then they get fired. So Stephen Cook, he's a very popular computer scientist, was actually, didn't actually get tenure at UC Berkeley in 1970. In 1971, he actually published this famous paper about the NP-complete problems. And then Berkeley actually tried to hire him back and he denied it. Okay, so he came to U of T, and in 1982, he actually won the Turing Award, which is the highest prize in computer science. Okay, so yeah, sometimes you get rejected at certain areas, but like it opens up a lot of other doors. So yeah. Why I mentioned this, because we are studying one of these NP-complete problems, and it's a very computationally hard problem that we know we cannot find an optimal solution for. And I'm trying just to motivate why we can't find the best solution in this milestone. So it comes down to trying to find heuristics. Good guesses that can get us good enough solutions within reasonable time. One thing I forgot to mention is that there is a time constraint in your milestone, which is 50 seconds. So you are required to find a solution within 50 seconds for the extreme cases. So we have like up to 200 deliveries to make with like 20-something depots to choose from. Okay. So let's think together. Anyone has any good ideas to how to like find good enough solutions? There is no wrong answer here. Like these are all, again, ideas that some of them might be good, some of them might be not, but like it's a good way to actually start thinking about this. Yes, go ahead, Arne.
I know we just said that you probably shouldn't try to find every possible combination, but you can greatly reduce the number of combinations if you just implement some logic. Like if the very first node or very first point that I'm visiting is a drop off, I have nothing in the truck, so like what am I dropping off? So it's like there's no
Okay. You are basically trying to cut down the number of combinations, right?
Yeah.
But even if you do that, you can still prove that it's still exponential, and you cannot loop over all of the combinations, right? So yeah, that's probably gonna drop the number of combinations by half, right? But half of like the whole that CPU time is still a lot, right? So yeah.
What if you only care about like the next move on the tower trend, and then you find like the fastest line, and then
Yeah.
you worry about everything else? Like
That's a good idea. So let's worry about what is like closest to us, right? Like what is, like where am I right now? What are the closest intersections to me? And I'm gonna choose the closest one, right? This is called a greedy approach. I'm just gonna choose the best intersection right now that I can see that might benefit me, in the hope that overall it's gonna benefit me at the end, right? So that's a very good approach. Yes, Dante.
What if at the very beginning you were to somehow figure out if an area where there's the greatest cluster of like pickup spots? So like knowing where most of the pickup spots are, you know where to start, because when you have most of the pickups, then you can just go to the delivery.
Okay, yeah, that's another good idea. So basically, I'm going to study all of the intersections first. I'm not going to visit any one of them yet. I'm going to see, can I divide my city into like areas where like I can combine multiple pickups at the same time, right? So these are very close to each other. It might be a good idea to pick them up first and try to drop them off, right? So again, that's also kind of a greedy approach. I'm going to choose like the area where it has like it's the most densely populated in terms of deliveries, right? So let's look at the first idea, to try and visit the nearest intersection first, okay? So I'm going to go from any depot. I'm just going to choose a depot at random. And from there, I'm going to go to the nearest pickup. I'm calling it here P, okay? And then in a while loop, while there are still packages to deliver, what I'm going to do is that first, I'm going to drop off the package at its delivery drop-off location, the one that I picked it up. And the second, I'm going to update P to be the next So wherever I go and drop off a delivery, I'm gonna look at the rest of the deliveries, and I'm gonna choose the pickup that is closest to me from that location, right? Again, this is called a greedy approach, and I'm just choosing the one that's closest to me. And I keep doing this until all of the deliveries are made, and then after I end the last drop-off, I'm just gonna look at all of the depots again and try to find the depot that is closest to me, okay? So let's look at the time complexity of this. To go from any depot to the nearest pickup location, what do you need? Here you need first to find to loop over all of the depots, and then loop over all the delivery intersections to choose the one that is nearest to that depot, right? So you need O of D times N to find the best one to start at, right? Okay, and now we have N iterations because we have N deliveries to make. And in each one, we're trying to find the next closest pickup location. And that's also an O of N problem, right? Because we are going to loop over all the deliveries again and try to find the pickup intersection that is closer to me. So after that, from the last drop-off, I know where I am. I want to choose the closest depot location. And that's also a O of D because I'm going to loop over all of the depots. So the overall time complexity is going to be O of D times N plus O of N times N, which is N squared, plus O of D. So overall, you can remove this O of D because it's not affecting asymptotically this. And it's O of D times N plus N squared. Okay, so that's the overall time complexity of this. And that's assuming that we can find the closest intersection in a constant time. But we're actually running, what are we doing actually? We're actually doing it to find the closest intersection. We're running the find path algorithm from milestone 3, right? So it's not constant time. Okay, so let's look at the solution for this. So for each depot, we are first going to evaluate what is the closest pickup intersections for me here. So for this one, we're going to loop 4 times. For this one, we're gonna loop 4 times again, and for this one, we're gonna loop 4 times again. So 12 times in total, just to find where am I going to start. Okay, so let's say that this is the shortest one, so I'm gonna start here. So I visit A first, and then what is closest to A here from all of these? First of all, we're going to drop off A and then continue. But let's look at what is the time complexity of the M3 function? We said that if it's a very good implementation, it's going to probably take us 100 milliseconds, right? Like 0.1 seconds. So to just find the initial solution, to just find the initial intersection we're going to start at, it's going to take us 0.1 seconds times D times N, right? O of Dn. And that's what? 100 seconds for a problem of size 100 deliveries. That's already too long because we said that we need to find a solution within 50 seconds, okay? Sorry, you had a question? Alex. Yeah.
What if instead of like calling find path to estimate, you estimate similar using to like the restart approach of like taking the
distance
and divide it by like some constant?
That's a good idea. Yeah. So instead of trying to find using the M3 algorithm to find the path, I'm going to try and estimate geometrically which intersection is close to me. And I'm going to go into this in a little bit. So that's a good idea. You're simplifying the 0.1 second and replacing it by a constant. So in this case, you are left with much smaller time to find the initial intersection. Okay. So in a similar manner, we're going to go into this in a little bit, but in a similar manner, let's look at the overall time complexity of the algorithm, right? So we said that the overall time complexity is O of Dn plus n squared. And say we have D equal to 10 and n equal 100, and let's say that the time, so we are basically multiplying some number by this overall number, which is 11,000, right? This C will represent the time is going to take you to find what is closest to me, right? Either through milestone 3 find path or like through like geometrical distance, okay? So if you call M3 find path to evaluate each possible travel time, again, let's say it's 100 milliseconds, this is going to take us 1100 seconds, right? Which is too long for our case. We are required to find a solution within 50 seconds. Okay, so as your friend said here, we can estimate the travel time by the geometric distance. We know it's not accurate, it's probably not the best travel time, but again, all we are doing here like are heuristics. They are kind of educated guesses to try and guide the algorithm towards a good enough solution. So let's estimate the travel time by the geometric distance. Just measure the Euclidean distance from all of the intersections to where I am right now. And that's considered a constant time, O of 1. Why? Because it's just a mathematical formula that you're gonna plug in instead of like an actual algorithm that you're looping over intersections. Okay? So let's say that constant time takes 10 to the negative 7 seconds, right? That's a very short time to just run the formula. And these days, computers are pretty fast in doing mathematical formulas, okay? So that time, the overall time drops from 1100 seconds to around 1 millisecond. So you found the solution within 1 millisecond, and that's more than fast enough. That's actually very fast for our milestone. Like, we are required to find a solution within 50 seconds. But what is the catch here? It's probably not a good solution, right? Like, we probably need to find better solution. But so after we find the delivery order that we want to travel with, then we're going to call at the end the find path function on the final solution, because we are required to return like what, a vector of paths. So, and that's around going to be like, let's say for the largest case, 200 calls, right? Because we have 200 deliveries. So that's around 20 seconds with 0.1 second. So we found a solution, a very good solution, within 20 seconds, right? So that's a good start for this milestone. Okay, so let's look at the example again. So we decided that we're gonna take A1 because it's from depot 2 because it's the closest. And then we're going to drop off A1. Then from A1, drop-off location, we're gonna choose the intersection that is closest to me. Okay, so in this case, to pick up C1 is the closest. Pick up C1, go drop it off all the way on the other end of the city. And then pick up B because it's closer. It's closer than, what is the pickup of D? It's closer than here, okay? And drop off B, pick up D, and drop off D, and then choose the depot that is closest to me, which is in this case, this depot 1. Okay? So it's much better than using the given order of the deliveries or choosing just a random order of the deliveries, right? We saw that it was like going back and forth across the city. In this case, we only went like once back and forth, right? But can we do better? Anyone has any ideas? Like, looking at this solution, is this a good enough solution? Or like, can we do better, intuitively speaking? Yeah? What can we change in this to make it better? Exactly. That's true. Yeah. So the handout tells us that we are allowed to pick up as many deliveries as we want, right? Like it doesn't have to be like whenever we pick up something, we'll have to drop it off immediately. The only constraint we have is that we have to in order to drop off a package, we should have picked it up first sometime before, right? Okay, so we can actually improve on this by just changing the order of visiting the intersections within the loop, right? Let's call this heuristic 1++. So go from any depot again to the nearest pickup location P. And in the while loop, to visit all the deliveries, first we're gonna say that P is going to be the nearest legal pickup or drop-off, okay? It doesn't have to, so it can be either a pickup or a drop-off. I'm just gonna choose the nearest one to me, as long as the solution is legal. So if I'm gonna visit a certain drop-off, I have to check that I've picked it up before, right? And then I'm gonna visit that and continue looping. So it doesn't matter that if I'm dropping off or picking up, I'm just gonna choose every time the closest one to me. At the end, I'm gonna choose the nearest depot to end the day. So let's look at the time complexity again. This is O of dn again here. And then 2n iterations because I'm gonna visit 2n intersections. In each one, I'm going to do O of n to find the closest intersection, and then go to the nearest depot, O of d. So overall, it's the same time complexity. It's probably a bit slower, like in terms of constant multiplier, but it's definitely going to give us like a better solution than the previous one because we're not dropping off every delivery we're picking up immediately, but we're trying to find the packages that are closer to me to pick up first. Okay, so let's look at the solution again. So again, we start here at depot 2 and then go to A1. So instead of going to drop off A1, which is very far, I'm gonna first pick up D as well. Why? Because it's closer to me. And then what do I do here? So from D, we choose that we're going to drop off D because it's closer to us. And from this drop off, I'm going to visit B, pick up C, drop off A on the way, drop off B, and then go all the way to the other side of the city and drop off C, right? And then finally end at this depot intersection because it's closer to us. So we can see that we kind of looped over all of the intersections in a circle or like an oval, instead of just doing this cross-city traversals, right? This is done by only just changing one thing in the algorithm, right? Just changing what is the next next intersection I'm going to visit. So you will notice that in milestone 3, most of the heuristics that you're gonna try are like changing like probably 10 to 20 lines at most to actually find a better heuristic. Maybe you have a much smarter algorithm that you have to develop, but that's fine. Like, there are actually ways to change the whole algorithm. So not much more code, slightly more CPU time probably because of the extra constant time, but overall better quality than the previous one. So that's a good idea. Okay. So the approaches that we've looked at so far, these are called greedy approaches, okay? And greedy algorithms are a popular set of algorithms in computer science that are based on the fact that I'm always going to choose the next best thing that I can see, okay? For example, Dijkstra, which is in its wave expansion, it's actually a greedy algorithm. Why? Because in each time we're deciding what node to visit next, we're choosing the node with the lowest travel time, right, from the candidate pool. So greedy algorithms sometimes can prove optimality, for example, in the case of Dijkstra. Sometimes they cannot prove optimality. There are a lot of problems. There are other set of problems called dynamic programming problems, in which case you cannot use greedy algorithms or you cannot choose just the next best thing in order to find the optimal solution. All of this will be, you will be taught in ECE345, but I'm just gonna give you giving you a sense of what kind of heuristics we can have here. Okay, so again, in greedy, we're going to choose the best decision you can make now, and you will never go back and change your decision. Once you choose something, you cannot change it back. Greedy algorithms are generally fast. We saw that we can find a solution within 20 seconds overall, but often they don't give you the best solution. There are smarter variants where you can use guesses of what may happen in the future to make a better decision, but I'm not gonna go into that. Again, this is just an introduction of what greedy algorithms are. Okay, I think these are the slides I had today, but like we have still more time, so I'm gonna go into the next set of slides. Any questions first before we continue? Okay. Okay, so the next thing we're going to talk about is how to efficiently estimate the travel time. So remember that what we just talked about is that we're going to use the geometric distance to estimate the travel time and only call the find path at the end, right? So that saved us a lot of CPU time because to find the geometric distance, again, all we had to do was just do a calculate a mathematical formula, right? This is a reasonable solution, but it's probably not going to be very accurate because we saw that like when we discussed A star, sometimes relying on the geometric distance might not be the best thing to do, and you have to actually look at the travel time. Actually, and remember, like when there was like a blockage around the highway 401, and we needed to go around it. So actually relying on just the distance might not be a good idea to estimate which closest to me. So it might cost us some more quality. So can we find better ways to estimate the travel time? Yeah, this is the example I was talking about. So remember this, like when we wanted to go from one intersection to the other across the highway, if we just rely on the geometric distance, this is probably going to be like 300 meters over 60 kilometers per hour estimation. And while in real time, it's probably much higher because we have to loop over around the highway and go to the bridge that crosses us, and then loop around to get to the intersection. So our estimation might not be very accurate, and it will hurt the quality of our final result a little bit. Okay, so we need to rely on the fact that can we use milestone 3 algorithm somehow to estimate the travel time while not wasting much in the actual heuristic that we're using. Any ideas to do that? Yes. But again, this is pretty close, and we cannot use the milestone. Sorry, you're saying to use milestone 3 for the closest one. Okay, so yeah, you probably can cut down the travel time by a lot. Sorry, the travel time estimation by a lot, and probably gonna get a good solution. Yeah, you can try that. That's actually a good idea. But we can go one step further. Can we completely rely on the travel time of milestone 3? We saw in the previous, a little earlier, that if we actually keep doing this inside the algorithm, it's gonna take us around 1100 seconds. But are we required to do this inside the algorithm itself? Yeah, one idea is to prefetch things, right? So we're going to calculate the travel time between any two intersections beforehand. So let's look at this. This is called memorization or memoization, okay? So pre-compute all the shortest path you might need, right? What are we given here? We're given 200 intersections, and in our algorithm, we might visit all of these intersections in any random order, right? So we might need to find the travel path from any intersection to any other intersection. And that's like around what? To n squared calls, right? So let's try to pre-compute these first. Then just once we need them in the actual algorithm, we can just look up the delay by and that's an O of one axis because it's just an unordered map that you can hash into. Okay, so we build this big matrix from every intersection to every other intersection. We're gonna calculate the travel time using M3 algorithm beforehand and use that matrix during the algorithm. Is that clear? Yeah, okay. Okay, so now let's look at how many shortest path we need to pre-compute. Again, if we're using the same algorithm in Dijkstra, it's like what Dijkstra does is like single source, single destination. We're going from one intersection to one other intersection, okay? And we need any delivery location to any other delivery location travel time. So that's around, that's a lot of calls. So that's around 40,000 calls, right? Because we are doing O of n squared calls to build this matrix, right? We have n intersections. So plus any depot to any delivery location, so that's around another 2,000 calls because like if n is equal 100 and d equal 10, that's another 2n calls. Okay, plus any delivery location to any depot, but that can be actually, that's another 2,000 calls. So we can see that in total we have 43,800 calls to find your path. And if we do that, if we do the math on 0.1 second per call, that's going to be 4,000 seconds. That's too slow. So it's actually too slow to build that matrix if we're gonna do this just by using milestone 3 itself, right? So we have to improve milestone 3 a little bit in order to be able to cut down this time a lot. I think we have 1 minute left. And the idea to do this, I'm not gonna go into the details now, we can discuss it in the next lecture. But if you notice in milestone 3, what Dijkstra does is that it builds the wavefront expansion from the source until it reaches the destination, and then it stops, right? But if we can continue expanding in the same call of the algorithm, we can find actually the path to all other intersections within the same call. And that cuts down the number of calls that we have to call